Okay, so now I'm continuing until the end of the course. I hope you had good time meanwhile. And today we will continue looking or start looking into the independent component analysis. Perhaps briefly because the history of so independent component analysis is one of the old methods um, in machine learning. Okay, it's one of the old methods in machine learning. It was developed in the early 90s. Some results were already in the 80s, and then there was a book in I think 99 by three Finnish authors, Erkki Oja, Aapo Hyvärinen, and I don't remember. Well, it's the book we have on the course, right? So it's the book we have on the course. Aapo Hyvärinen is my friend, and I'm going to be using partially his slides today. Okay, Juha Karhunen is the third author of that book, and at the same time, Aapo Hyvärinen came up with a fast algorithm for computing ICA, which is independent component analysis, and that became very famous. So actually, if you download the Python library for ICA, it's probably going to be using Aapo's algorithm, and it's a very cool method. So I guess yeah, I just still need to get my slides. Yes. Sorry about this. Okay, so we started the overview and also this. Okay. Okay, so independent component analysis takes data where signals are mixed. So ICA is an unsupervised machine learning method, which means that it analyzes data without any prior markers. There's no labels. You just what happens is that you have three sources of data. So here are some sound data, for example. A very common application is with sound. And four. I'm sorry, four. Four. I somehow didn't realize that this is one of them. And all these are mixed linearly. So this one is some sort of a weighted sum of all of these four. This one is also another weighted sum of these four, and this is the third one, and this is the fourth one. So for example, if you have four sound sources, like you have a guitar, somebody singing, you have noise from the audience, or maybe this is the noise from the audience, and these three are like, I don't know, guitar, a voice of a person, and of a singer, and then I don't know, another musical instrument like a saxophone. Now they're all mixed, but we are taping this with four microphones. Each microphone obviously gets everything, but they have different distances from the different things. So we can separate using ICA back all these tracks so that we can delete the noise, and we can also separate the different instruments. And if you go online and you go and check, there's a lot of examples where you can just listen to these tracks, and you can see how well ICA actually does. Is doing a pretty good job. You can do it also with pictures. So sometimes pictures are, if you mix pictures, just like overlap pictures, and you overlap them in different ways, then you can reconstruct the original picture. So let me see if I can find just some example. Okay, so this looks like an example of that. Okay, so here we have pictures, and okay, I don't know. Looks like something is going on here. So that's pictures of faces. Ah, yeah, here. Okay, so okay, like this. Okay, so no, you get the idea. So you mix pictures, and then you can reconstruct them back. That's the idea. And I'll just show you how we get to equations from this. So imagine we have sound sources, I don't know, like this, in the environment. And then we have four microphones. Just for the sake of the argument, let's have two sound sources and two microphones. And we have this distance. Let's say this is 1, 2. This is 1, 2. So this distance is 1, 2. This distance is supposed to be straight, is 2, 1. This distance is 1, 1, and this distance is 2, 2. Okay. Now sound decays as a square of the distance. So the weights we will be having are given like that for all of them. And so then what we measure here are x1 and x2. So we get a vector, which we will be treating as a random variable. So we receive a vector, and it's mixed. So the first microphone gets a weighted sum of the signals. So the signals is S1 and S2 for signals. S1 plus W1 to S2, and W2 1 S1 plus W2 2 S2. 2, right? So this is what's happening because this, for example, this sound source is weighted by W11 and etc. And so we can see here already that this is a matrix product. We just move it a little. Oops. Okay, and so we can see that this is actually some matrix times S. Now I messed up because I was supposed to be using letters A for this. I'm going to be using A for this. So this is what I wanted to actually write. So it's some matrix A. I'm going to be using W for something else. Okay. Okay, so this is the problem, and okay, so let's go back to the slides. We'll get back to this later, and we will analyze this, and hopefully we'll have time to prove that everything works. Sorry. Okay. If you know what is principal component analysis, you don't have to know, but if you know, then just if you try to do this with principal component analysis, you will fail. It's just not going to work. And the way ICA works is that it uses the idea of statistical independence. So in the last lecture, Nicoletta told you about the central limit theorem and the kurtosis, and that if you have a lot of independent variables and you sum them up, then you will be approximating normal distribution. On the other hand, the kurtosis of the normal distribution is constant. It's 3, or if you use the excess kurtosis, then it's 0. And it's because the normal distribution is completely determined by its mean and variance. And so the kurtosis, the higher order momentums don't change. Okay, so here is basically the same equation I just wrote in my virtual blackboard. This x is the measured signal, and these s are the real assumed signals, and these a's are those weights. So we have this kind of matrix decomposition. This A is called the mixing matrix because it mixes the signals. And these SIs are so-called independent components. So the idea is that we assume that these signals are independent, and they are, so statistically independent. So if you're listening, to music and you have a guitar and so on, the patterns, if you look into like a small sound window within half a second, the sounds coming out from the guitar are going to be completely statistically independent from the sound coming from any other source. Even if they are playing the same melody, and you could think they might be correlated, they're not really statistically correlated because the overtones are different, the tremble, the type of vibrations that come from these different instruments are really so different that even if there is a slight statistical dependence, it will not be influencing in any way this algorithm. Okay, so it's actually pretty surprising that you're able to, only from measuring this result of this matrix multiplication of matrix by a vector, you can actually deduce backwards all of the variables. So you're measuring 2 variables, and there are 6 independents. So there, if we're in the 2 by 2 case, right? If you're higher dimensional case, even more. But in the 2 by 2 case, the one that I had on my blackboard here, we have we're measuring two variables, x1 and x2, but we have 6 independents. We have a11, a12, and 200, and we can up to multiplicative constant and maybe inverse, we can recover all of them. And because the multiplicative inverse we can normalize, so it goes away, and the inverse, meaning by inverse here, I mean just multiplying everything by -1. You can easily, if you end up having sound, which is the inverse of trumpet, you immediately know which one is the real trumpet and which one is the wrong trumpet. So this is the inverse of trumpet, so it also doesn't really matter. So we can actually recover all of these variables. It's pretty amazing. And it's all based on the non-Gaussianity assumption. So if these signals are distributed as a Gaussian distribution, then this will not work. It will only work if these variables are distributed in a strange way. But all these kind of, let's say, sound or any natural variables that you measure usually are not distributed in a Gaussian way, unless you're measuring really noise. And noise is essentially the only thing that is really distributed as a Gaussian Okay. Yeah. So this slide is exactly what I just said. So you have to assume that these signals are statistically independent. You have to assume that they're not Gaussian, not normal, not normally distributed, and it's a good if your number of signals is the same as the number of measurements. So in our case, in our example, it was the number of microphones and the number of original sources. If they're the same, then this thing works better than if there are more sources, for example, than measurements. Yeah, this idea was originally proposed in '94. It was mathematically oh, I don't want to say prove, but yeah, prove maybe in a way, like, or kind of realize mathematical idea was I realized it. And okay, this is we're going to skip. Okay, so yeah, so like I just said, most natural signals will be independent and non-Gaussian, and it means that different types of invariants that you can calculate from a probability from a random variable like this are going to be different than those for normal distribution. So for normal distribution, if you know the variance and the mean, and you can always normalize your data so that the mean is 0 and the variance is 1. You can always just normalize it. And because you normalize it, if it's Gaussian, then it's completely determined. Then you know the kurtosis is 3 or 0 in the excess kurtosis, etc. But if the original distributions are not Gaussian, there's some other parameters that you can measure, and you can basically detect how Gaussian these variables are. Okay. Okay, so here are some examples of why it's natural to assume that variables are not Gaussian. So this is some typical sounds. This is some non-Gaussian noise type of thing, or maybe some sort of a sound source as well. And we can see that this one, for example, has very much mass here in the where you would normally have tails, so it's very non-Gaussian. These are the opposite, spiking. a lot of stuff in the middle, but a very small small amount of stuff in the tails. Same here. So I don't remember which way around it goes, but one of those is kurtosis negative, the other one is positive. Maybe this one would make excess kurtosis positive, and this ones would make it negative, but I'm not sure. So yeah, a very simple example is when you have two uniform variables and you mix them, you can, from this, you can recover with ICA back to the square. So you find basically the vectors here which point in the direction of independence. So before we go much more further, let me just explain this a little bit more with a picture. So imagine, so this is a very simple example. We have this exactly the same. Say we have this, sorry, let's try to make it straight. So we have this square type of data. And then we transform it with some mixing matrix, like in that picture, into some sort of thing like that. So this was some matrix that, and now the ICA, the job of the ICA is to find the vectors which point in the direction of the independent components. And the way it works, so you take some vectors. Let's say you take some vectors, and let's say you take some vectors which are not independent. So, for example, instead of those, suppose you take, I don't know, this vector and this vector, and well, let's take one. Let's take one for the sake of the argument. Suppose you start with this vector. Why is this vector not going to have a it's actually going to have a high kurtosis, high absolute value of kurtosis. Sorry, mixing things up. It's going to have small kurtosis, close to zero. I'm talking about excess kurtosis. So from now on, whenever I say kurtosis, I mean excess kurtosis. Let me just remind you, excess is from last lecture. Excess kurtosis is defined as the fourth momentum. So it's the expected value of the fourth power, and we normalize it by subtracting the variance squared times 3. But if we assume that the variance equals 1, so it's normalized, then this is just 1. So for a normalized variable, and by normalized, I will just always mean that the average, the mean is 0, and the variance is 1. And the way we can always get this is that if we have any variable, we just perform this trick, and then this new variable will have 0 mean and unit variance. Okay, so when this is the case, then the excess kurtosis is simply defined as the expected value of the fourth power minus 3. Okay. We will actually need this more general definition at some point, but at this point it doesn't really matter. Okay. So suppose we took this vector, and why is this kurtosis going to be small? Because it corresponds to this vector here. And if we look at this, at this distribution rotated, like from the point of view of this vector. So imagine we rotate the whole thing so that this vector is vertical. So this vector is vertical means that these points are like this, right? Essentially, it's the sum of two uniformly distributed variables, and it is much closer to the normal distribution than if you had a vector pointing directly vertically here or horizontally, in which case you would have something like this uh, when you rotate it. And now this is much further from the normal distribution. So kurtosis here is going to be much larger. How do you do it? Much larger than 0, while here is going to be closer to 0. And so by maximizing kurtosis, we find a vector where these different variables are not summed up. And why in this always works is because of the central limit theorem. Because whenever you sum up independent variables, you get closer and closer to the, in fact, super fast, as you can see. Summing up two uniform variables already gets you much closer to the unit distribution than not summing up at all. So we can maybe even see some cool pictures. I would imagine. No pictures. Here, pictures. Okay. So the more you sum up, no, this is not a good picture. That's very surprising. Okay, here. Like here you can see one uniform variable, two uniform variables, three uniform variables. With three uniform variables, you're almost indistinguishable from a normal distribution. So this is why kurtosis is such a powerful tool for detecting independence. On the other hand, the other assumption, so what's it? Sorry, not the other assumption. If we have this original sources are Gaussian already, then there's nothing you can do, because then you sum up Gaussian distributions, they're still Gaussian. There's no way the kurtosis, excess kurtosis is 0 in both the original variables and the new variables. You cannot separate. Right, so what I just said, averaging many independent variables will make it closer to Gaussian. And so when you have a mixture, it's going to be more Gaussian than the original components. If we look at the equation here, when we multiply this by, so we're going to be trying to find a matrix W. So this is why I didn't want to use W there. We're going to want to find a new matrix W, which is the inverse matrix. And so we multiply those, and it's the same thing as multiplying W by A by S. So it's sum matrix B1 S1 plus B2 B1 1 1 2 B2 1 2 2. Okay. So where B, this is just B. So now you can see that if it's not, okay, there are four options for B basically. If B is not one of those, so identity matrix, that's this matrix or this matrix. Okay, three options. Okay, no, one. Four options, just like I said in the beginning. Okay, so these four options are the only ones which leave only one of those S1 or S2 in a given row. If it's not of this form, then both and assuming that we normalize everything, so it's it's the norm of the matrix is one, so there are no other options. It has to be a rotation matrix basically. If you have any other matrix, then you will have a mixture, and because you have a mixture, then you have a kurtosis higher than smaller than it could be, closer to zero. Then as soon as you have a mixture, you're closer to Gaussian. So that's why maximizing kurtosis is going to be the key to this thing, maximizing make it very precise, maximizing the absolute value of the excess kurtosis. And more generally, maximizing non-Gaussianity of this. So this WIXI corresponds exactly to multiplying this X with this W. Here's the same example, which I already showed in my Blackboard. There's other ways to measure non-Gaussianity than kurtosis. And if you come up with a new one, then you will probably come up with new algorithms for ICA. And by the way, ICA is not the only place where measuring non-Gaussianity is important. So another one is called differential entropy. Then there is, if you look at the book, which we have in our Moodle, you will see that there's a lot of different methods. And not only have different measures for non-Gaussianity, you have different ways to optimize them. So gradient descent is one, and this Hyvärinen's algorithm, fast ICA, is based on some kind of fixed point algorithm. I actually don't know how it works. Not part of this course either. Some examples of applications, not only in sound, also in, let's say, neuroscience. Very common thing with EEG or magnetic, so either electric encephalography or magnetic encephalography. You usually measure very mixed signals, right? So you're putting these measurement units on your head, and each unit records, just like the microphone, it records a mix of stuff that's coming out of the brain. And each of these units will record something that the next one also records, but weaker. So everything they record is kind of overlapping all the time, but you can deconstruct the original signals using ICA. So a very important tool in neuroscience, also applied in fMRI, and applied all across the board. And this is not something you can get with deep learning, because deep learning is supervised and this is unsupervised. So here you don't need labels, you don't need any data, no training data. I mean, some data to be able to analyze it, but you don't need any training data. You just record stuff from your brain and you apply ICA to it, and you get very, very clean pictures of what's going on. I would imagine that you could stack ICA and make like deep ICA. I have no idea what will come out of it. That could be a thesis project for someone, or just fun exercise to think about it. I don't know. Okay. So I'm basically done with the first part of the lecture. What if, do you have questions? Does anyone have any questions? Okay, since nobody has any questions, I will now make some announcements. Although, since only fraction of you is here live, I will have to make them again. But so next week is a very special week. The Monday lecture is at 10 a.m. instead of 12. And then on Thursday, we have a lecture because, look, Friday is the Independence Day of Finland. This is why it's all happening. They have to reshuffle the whole schedule of the whole university. So Monday lecture is at 10. And then what else do we have? I don't even remember. Um,
I think there's a Tuesday lecture or something like that.
yes, Tuesday lecture. Here in the announcements, there is detailed schedule, which I made. Yes, Tuesday. Oh, at 8 a.m. I'm going to be alone, and I'm coming to Oulu, so it's not going to be online. It's going to be live. So better be there or be square. And then we have a Thursday. Is like already the next week lecture is moved to. I mean, the following week lecture is moved to next week Thursday. So and it's going to be at 4 p.m. So we will cover a lot of material next week. It's going to be 3 lectures, and I'm going to be in Oulu, so I'm going to deliver all of them live. Okay, that's announcement number one. Well, I don't really have other announcements. I just want to remind you that we are giving points if you find mistakes in our material. Um, any mistakes in exercises, solutions, slides, lecture material, if I say something wrong, and we have already given total like 20 points or something, so you can really get them. What else? We have the anonymous chat. We appreciate if you give us feedback. Of course, we appreciate if it's polite. But it's anonymous, so you can do whatever you want. And I appreciate if you give feedback for me because it helps me to improve. Both good feedback, bad feedback, everything is welcome. Thank you so much, and see you in 15 minutes. Just realized that I was sharing my screen all the time, but that's fine. Okay. Um, let's continue. Right. Okay, so in this lecture, we will go a little bit into more details, and we will basically show all the details of how it works in the two-dimensional case. So first, a little bit of a reminder. Um, so this is the excess kurtosis. In case of unit variance, collapses to this. If it's Gaussian, then this is going to be 0. If it's, oh yeah, we call, as I said before, normalized means this, 0 mean unit variance. If it's not normal, if it's not normal, I mean normalized but not normally distributed, then it's very unlikely that the kurtosis is 0. It could be in very strange cases, but it's so unlikely that if you measure natural occurring phenomena, then non-Gaussianity really strongly correlates with having kurtosis not equal to 0, excess kurtosis. Whenever I say kurtosis, from now on, I mean excess kurtosis. Okay, just a little mathematical prep before we get to do what we want to do. There's a property of vectors which I figured out this morning. Uh, it's so if you have two vectors and you take dot products like this, A, B, B, A, and of course it would be A, B, A, B, then you can actually rearrange them like that and get A squared, B squared. It's not absolutely trivial. Why? I give you an example. Imagine you could have vectors A, B, C, and D in such a way that A, sorry, let's make it this way. B dot A times, now these are just real numbers, right? These are dot products, times D dot C is not the same as B I don't know, like if you put and compute it in a different order, you don't get the same thing. So because B and A are not orthogonal, D and C are not orthogonal, so these dot products are not going to be 0. So this product is not 0, but A and D are orthogonal, so this is 0, so this is 0, right? So we cannot always do that, but if A and B, so if A and D are the same and B and C are the same, you can actually do this. Proof. Put them in a matrix so that take the vector A and make a big A matrix where the small a is just the top row and the other entries are 0. Do the same for B. And now, if we compute this product C like this of these matrices, then the leftmost topmost element of that matrix is actually going to be the left side of this equation. Take another matrix D, where you multiply those same matrices like that. And now the leftmost topmost element of this matrix is going to be equal to the right side, not right side, but it will be equal to this. Okay. Now, matrices are associative. So for matrices, we know we can shuffle, not shuffle the order, but we can change the brackets. A, B, B, A, B, B, A is all the same for matrices. There's no difference. So then we know that this C11 and D11 must be the same because these matrices are actually the same matrices, C and D. And because these are the same, now we know that this is the same as this, but this B times B is just a real number, just a scalar, so we can take it out, and then A times A becomes A squared, so we get this. Okay, funny observation, which we will need. Another observation is that if we have a random variable, which is normalized x, and a constant vector, now we use this observation for the first time actually, so we see that the variance of this dot product is just c squared, because, well, okay, so let's open up. Variance is the expected value of the square. Open the square. change the order here. Now, using the previous slide, this becomes this, and then because c is a constant, c squared is a constant number, just take it out. And this is 1 because we assume that x is normalized. Feel free to interrupt if I'm going too fast or something is unclear. And this, I believe, was in the last lecture. You have kurtosis satisfies this property. It's linear with respect to sum and not linear with respect to constants, but you can take out constants like this, become power 4. Essentially, this, by the way, is just taking out this constant, but I wanted to prove it separately because now this is not a number, this is actually a vector. And for this, you needed this strange thing here, okay? All right, so in two-dimensional case, this is our ICA problem, as you remember from last lecture. S1, S2 are the signals coming from two different, let's say, sound sources or from two different brain imaging sources or something. And you multiply them by this mixing matrix, which is unknown, and you get a signal x1, x2. You get the observations x1, x2, and this is denoted as the matrix A, and this is the vector S, and this is the vector X. Okay, so we want to find another matrix such that when we multiply this A from the left, then we get identity matrix. So essentially this W is going to be the inverse matrix. And once we do that, we know that when we multiply our observation by this W, we will get back this original signal because W times X is the same as W times A times S, and we just assume that the W has been found such that this becomes identity matrix, so this is identity matrix, so it's just S, okay. Now, for the sake of simplicity, there's a lot of theory about normalization and stuff. We're going to skip stuff, but just I want to show you the basic argument in ICA. This is a no-brainer. So we normalize our observation. But because we normalize our observation, we can also assume that our matrices are orthogonal, not orthogonal, they're rotations, essentially. But not, sorry, it's not, I take it back. I don't want to say they're rotations. Do I say that? I'm not saying they're rotations, but I'm saying that their norm is 1. I'm not going to go into details what this means, but essentially the norm of a matrix means that if you multiply it by a vector, or by a unit vector, then the largest possible vector you can get is also equal to 1. So it's not exactly rotation. I'm sorry. This is a mistake. But the norm of these matrices is going to be equal to 1. Basically, that's the idea. Okay, so it's not very important, by the way. It just makes algorithms work better, and also it will make one of my arguments later a little bit easier to make, just to show that this thing, how well this thing works. Okay, so let's define these vectors y1 and y2, which are these 2 rows of this matrix, which we will get not matrix, just components of this vector, which we get if we take our observations and multiply by this W, which we're searching for. W. And we will show that, so now more formally, we will show that maximizing kurtosis of y1 and y2 is actually a good candidate it's a good candidate for the solution. Since y1 and y2 depend on different sets of variables, so x1 and x2 are not variables now, they're our observations, they're fixed. Our variables are w11, 12, 21, 22. So this depends on w11 and 12, and this depends on w21, 22. So they depend on different sets of variables. So we can maximize them independently of each other completely. So we don't really need, we can just assume that we're looking at one of them at a time. Once we know that maximizing these is giving us our answer, we can use gradient descent. That's the idea behind the standard algorithms of ICA, not behind the crazy fast algorithms. But essentially, you get the idea. Once you need to maximize something, gradient descent is like the first shot you would try, and you can do it like this. You can actually take the derivative of this kurtosis. You can imagine it's a fourth power, blah blah blah, etc. Okay, so let's denote this W times A by a separate letter B. So this is the matrix B, and so now we have that Wx is the same as Bs, B times the signal. So because B is just this. And in particular, now we rewrite Y1 and Y2 as there's a mistake here, I'm sorry. This is supposed to be B. So I'm sorry, this is a mistake. Anyway, this is correct. So because as we saw here, our Y is just this Wx, and because we just defined that Bs is like this, so Y is like that. Okay, so Y1 would be, if we replace this by B, sorry, we should have to replace this by B and this by S. This by B and this by S. Then we get the correct one. Here is the correct one. This here is equal to Y1. Okay. So the excess kurtosis of Y1, which I just told you that we have to maximize. What is it? Well, we open it up like this, and then we use this formula, which we saw a little bit earlier. And then we see that the variance of Y, this is Y1. I'm sorry, again, this is Y1. So Y1, the variance of Y1 is equal to B squared. Now, look, you might be wondering why is this, but again, I'm using this trick that I showed you here in the beginning. This trick. See, variance of something times something that's C squared. So now the constant here is B. And S, so I said we normalize X, but then we also assume that these matrices are normalized. So we actually assume that our signals are normalized. And the trickstery, which you can read from the independent component analysis book, is that so you find these matrices assuming that everything is normalized, but then you have like this matrix only depends on a basically multiplicative constant, and you have now just one variable equation, and now you plug in the original non-normalized values of your data into this new equation, and then you get the non-normalized matrix. That's basically how it works. So now we assume everything is normalized. So then this S also has variance 1, and so we get this. Again, this is not very important, but the reason I'm showing you this is because then we get a constraint, because then we know that this is 1, and so it's on a unit circle. Again, here's a typo. It should be squared. I'll just change this b. Let's forget this part. What I'm saying in this line is that b is constrained to unit circle. What does that mean? It means that we're maximizing this, which is equal to the excess kurtosis of y1 with this constraint. Now, not all of you are probably familiar with Lagrange method, which is fine. We can actually go through it because I realize now that I'm out of material for this lecture soon. But the Lagrangian method is that if you have a constraint optimization problem, so you have a function that you have to maximize and you have constrained it to a certain level set. This is called level set. So it's like a set where some function of the same variables is constant. Then you can solve this by solving this equation. What is this equation? On the left side, we have the gradient of this function. And now I just shorthanded this kurtosis to K1 and the other kurtosis to K2. So if I take the derivative of this with respect to the first variable, then this 4 drops and the 3 and the power becomes 3 and this disappears. So the derivative of this with respect to the first variable is here. And the derivative of this with respect to the second variable is here. Again, this becomes 0, the 4 drops, and the power becomes 3. And on the right hand of this equation, we have a derivative of this, the gradient of this function. I can explain soon why this works. But maybe some of you have been to some kind of calculus class where you did this. It's very standard. It's a very standard thing in the engineering kind of curriculum. So if you didn't know it before, it will be very useful for you to know. Anyway, so this is the gradient of this, obviously, right? So the derivative of this with respect to the first variable here and the second variable here. And now, if you look at this equation, and from the Lagrangian method, we know that by solving this, we get the maximum points for this function. It's only a very unlikely situation where B11 and B12 are exactly equal when it is possible to find a lambda. Oh, by the way, also this kurtosis must be equal. Only when both K1 equals K2 and B11 equals B12 is it possible to find a constant such that these are equal. In every other situation, like you can maybe you can find all the cases where this would go wrong, but it's a zero measure, so to speak, zero measure set. It's like a super unlikely probability is 0 that it will happen. In every normal general case, this equation, so to find a constant such that these are equal, is only possible if this is equal to 1. I mean, all B11, B12, blah, 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 are equal to 1 or 0. Because you have power 3 on the left side and power 1 on the right side. So if K1 is not equal to K2, essentially that's what I wanted to say. Then the only solutions here are 1 and 0, which shows that if you maximize this expression with respect to b11, b12, and I have another mistake, this is supposed to be b11 and b12 over here. Anyway, this shows that if I maximize this expression, it must be a solution to this equation with some lambda. So then this might be 1 or 0. Okay, so what does it mean that they're 1 and 0? Let's go back and see. They're 1 and 0 means that it's only one of these components is left in y. And y is exactly what we get when we multiply x by w. So out of these several solutions, as I showed you before, if you do the same thing for y2, right? So do the same thing for both 1 and y2, you will get a matrix such that when you multiply, you will get one of these four, must be just zeros and ones, and then the norm of the matrix is 1. So there's no other options than having one of these four matrices, and then you just do some very rudimentary analysis, and you're like, oh, it can't be this, it can't be this, it can't be this, so it must be this. It's like out of four different options. And I believe that this classical, like any ECA algorithm, which you can find in a library, they will automatically exclude these two because they're singular matrices, and you can see it from the math. But they might sometimes give you the wrong one, like this one instead of this one. But then you just apply a regular transformation to get what you want. And usually what happens is like you see it from the result. In cases it's important. There's some cases where it's absolutely unimportant. So if you're using ECA to really separate the guitar from the voice of a person and the noise from the audience, yes, you want the right matrix, because otherwise your guitar will sound like something weird because it's inverted. But there are many applications for ICA where it doesn't matter, namely when you purify your data, like you prepare, it's like called pre-processing. Before you put your data into deep learning network, for example, very common practice, at least used to be, I don't know if it's anymore. It used to be very common practice, used to be 5 years ago. Very common practice that you first whiten your data and you put it through an ICA so that it's normalized, not only normalized, but also like the independent components are found, so it's easier to process for the deep learning network. The deep learning network will pick up on the signal much faster if the signal has been already separated as much as possible with ICA, just so you know. If sometimes you have a situation where you have a noisy data and you're applying deep learning, maybe try applying ICA first. Okay. Right. So we just showed that if you maximize these kurtoses, we showed it from here, you get a 0, 1 entry matrix, and you're done. Interestingly, by the way, I did this argument myself this morning. I did not see it in the book. I don't know if it is there. In the book, they have like let me show you from the book. In the book, they show like a much simpler picture, I guess because they want to be educational, but it's actually the same idea as the Lagrangian. So this is what they do. They say they use Q instead of my B. So again, but the Y is the same. The Y here is the Y1 of my slides. So, okay, so kurtosis is this, and they say, okay, now we have to maximize it with a constraint that this is on the circle. But then they don't go ahead and say anything about the Lagrangian. They just say, look, just as an illustration, assume that both of these kurtoses are equal to 1. So this kurtosis and this kurtosis, so the kurtosis of the original data, let's just assume that they're equal to 1. So that now you're having this uh, function. And now you ask how to maximize this function when you know also that this Q1, Q2 are on the unit circle. And then you geometrically can draw this level sets. And they look like this. So if you take, the Q squared plus Q1 squared plus Q2 squared, you get a circle. The Q1 to the power 4 plus Q2 to the power 4, then you get this. And so you get, as you can see, only 4 points where it's maximized. That's very interesting, by the way. Remember, I said in my slides that the kurtoses have to be different, then you get a solution. And now we see that even if they're the same, you also get only 4 different solutions. By the way, the 4 must correspond to these 4 different matrices that I showed you. So, but if they are different, then even with a more, is even more clearly, you just have this 0, 1 solutions. But if they are the same, then you can use it, which is very unlikely, but then you can use this geometric interpretation to see that they in fact also works. Interesting. Okay. I just wanted to show you another of these pictures here from the book. So here's a data set, a kind of an converse example. Here's instead of uniform distribution, you have this kind of very spiked distribution in both directions. And now if it's mixed like this, so we observe these components. So we observe projection to this coordinate and to this coordinate. We will see that these both of these projections are fatter than the original one, which is this. And they're fatter because, again, they're closer to Gaussian, even though they are not really Gaussian yet, but they are closer, and the kurtosis is smaller for both of these. And so when you rotate it to get the kurtosis back to 0, then you will get back, maximize the kurtosis, you will get back this original picture. Okay, I'm basically done with what I want to say. Maybe the last thing we can do is to go through the Lagrangian method. I'm just looking if there are some better pictures. I think they did a very poor job with pictures in this book. They could have added much more cool pictures. It's fine. Okay, no good pictures. Let's go a little bit through the Lagrangian method. I'm just going to cheat. Oops. So here we go. That's a good picture here. Okay. Here. So look at this picture. F is the function that we want to maximize. It's a function in 2 variables. In our case, it's the 4-degree polynomial that we have. We want to maximize that function, but we want to maximize it on some curve, red curve, which is given by this equation that some other function is constant. Now, in our case, I can draw somehow simultaneously. What? Here we go. Let's put it on top. Okay, so here we go. So f of x and y in our case was x squared times kurtosis 1 plus y, sorry, not squared, power 4 kurtosis 2. So we had b11, b12, but we can denote them by x. And the g of xy in our case was x squared plus y squared minus 1. So when this is 0, that's the constraint that we had. And then, so we want to maximize this f on this curve. Okay. If we are in a point where the gradient of this f does not point into the same direction as the normal to this g, suppose, for example, here in this point, let's take this point. So we can see the normal does not point exactly in the same direction as the gradient of f. That means that we can still go along this red curve higher up. Only in a point where the gradient of f aligns with the normal of g, that means that going along the g cannot increase or decrease f. Because normal means it's perpendicular. So if the perpendicular one is the direction where f grows the most or decreases the most, then going along the curve means that you go, you're flat. If you're standing on a mountain and you're looking to the direction where the mountain is like dropping the fastest, that's when you know that left and right is going to be straight. That's the idea behind Lagrangian method. So in order to maximize this f subject to this level set, all you have to do is to find a point where, or all the points where f gradient equals the normal to this g, okay? And what does it mean that it's normal? It means that the dot product of the gradient and this g is zero. Or the other way to observe it is to take the gradient of the original function g from which your curve came from. If you take the gradient of the function from which your curve came from, again, the gradient is going to be pointing exactly perpendicular to the curve because the curve is a constant curve, so that goes into the direction of zero gradient. So the perpendicular direction is always the maximum gradient. It's a simple linear algebra argument with the Jacobians, but goes beyond this course, but intuitively you can see why is the case. And so making those two equivalent here. And what does it mean that they point in the same direction? It means that they're not exactly equal. They might have different length. So there is some lambda, some constant lambda, such that make it them equal. And then if you find all the solutions to this, and you're on a good track finding the maximum minimum points of this f on constraint to the G. And that's what we were using to basically show that this method works. Okay, this part is not going to be part of the course. We're done. If you don't have any questions, do people have questions? So if nobody has any questions, we can stop here. So go home a little bit earlier, and see you on Monday at 10 a.m. live in L1, I think L9.